Thank you.
And I forgot to introduce Boo.
Oh, yeah. And so our co-presenter today is also, this is Boo as well. So thank you for that introduction, TD. If you know me, you know that coffee is a core part of both my personal identity and my personal brand. So we will do our best to keep this talk on schedule because I want to go get coffee as much or more than you do. So yeah, I'm Holden. My preferred pronouns are she or her. It is tattooed on my wrist. You can follow me on Twitter. You can also buy my books. I recognize some of the same people here from my last talk, so I'm sorry. But please, if you have a corporate expense account, buy several copies of High Performance Spark. It is the gift of the season. And yeah, you can follow me on GitHub as well, and I have the videos of my talks. Most of them are from previous Spark Summits as well. They're up on YouTube. And yeah, so in case you didn't hear this in the last talk, I'm trans, I'm queer, I'm Canadian, and I'm part of the leather community. And I want to remind everyone that we come from different backgrounds. We all write the same shitty code, like none of this stuff works. And if we work together, we can make something that looks like it works faster, and we can all go home and see our partners or spouses and have a nicer life. So be friendly to your coworkers. It's nice. Yeah, thanks. Oh. Thank you.
So I'm Nick Pentreath, and as Holden mentioned, we work together at the Spark Technology Center at IBM. I'm a principal engineer there, working on machine learning and Apache Spark, and I've been involved with Spark for many years. I'm a committer and PMC member on the project. I've also written a book, not as many as Holden, but it's called Machine Learning with Spark, and is available. And you can find me at MLNick on Twitter, LinkedIn, GitHub. So quickly, a little bit about IBM's Spark Technology Center. It was founded in 2015 to really try to advance Apache Spark into the enterprise and try to leverage IBM's broad enterprise experience and contribute core code and intellectual technical capital to the core project and surrounding ecosystem. So we're co-located with designers and a bunch of developers in San Francisco and around the world, and contributed the Apache System ML project to the Apache incubator. So who do we think you people are? Nice people, I think, from the previous talk, Holden's previous talk, and your applause right now. So you don't mind a few pictures of cats and other funny things. If you do, well, this may not be the talk for you. We assume that because we're at a Spark conference and it's now the second day, that everyone knows a little bit about Spark. It's probably some Scala and Python. And of course, you're interested in machine learning. You think it's cool, useful, and you're interested in extending ML. Or possibly you skipped the previous two talks about this topic at the summit. So what we're going to talk about very briefly, what are Spark ML pipelines, estimators, transformers, and then we'll work through how to actually implement each of those in your own custom components. We'll talk about Holden's new project, Sparkling ML, and try to garner some free work out of the open source community, and convince you to publish your fancy new model or transformer publicly, whether it's Sparkling ML, hopefully, or some other format. And of course, try to sell copies of Holden's book and my book if you care for that sort of thing. And yes, this is the third talk on this topic at the summit, but we have way more pictures of cats. So why should you care about Spark ML? Well, we all know that the machine learning pipeline involves taking data, doing some magic, and making money, right? Great. You can use it for deep learning, so you can raise a massive investment round for your startup. But really, Spark ML follows the kind of scikit-learn inspiration, and that is to provide a package of high-quality machine learning algorithms, which is great, because unless you're a deep learning researcher, you don't really want to be rolling your own things all the time. However, that's not really all there is to it. Most, if not all, of the work of a data scientist, machine learning practitioner is involved in processing data and getting it ready for feeding into that machine learning component. And that's really where pipelines come in. Feature preprocessing and the need to have the exact same set of transformations happen at both the training phase and at prediction phase when you deploy that model into production. And of course, if you implement everything using the standard API, any new tool or any new model that you want to implement that implements that API just fits neatly into that whole framework. And finally, it comes out the box with nice meta algorithms for cross-validation, grid search, evaluation, and so on. So we mentioned the need for Spark ML pipelines. The typical data science workflow involves taking data, transforming it through a few stages. This can be pre-processing, feature extraction, and then, of course, training models. So we can do that individually, but of course, it's much easier to just have a pipeline abstraction where we can put all of those things together. And we can treat that entire pipeline as a single stage. We can feed data to it once, and under the hood, it takes care of pushing that data through each phase in our pipeline or in our machine learning workflow. So what kind of pipeline stages are there? We have a transformer, which takes a data frame, a set of data, and transforms it into a new data frame. Typically, that involves just appending a column or a set of columns. And then we have an estimator, which is, effectively needs to see data, and then it creates a transformer, also known as a model. And that is really just a stateful transformer. So an estimator is something that needs to see all or a piece of the data in order to build that state, and then it returns you a model, which is a transformer that you can use on new data. So a pipeline is itself also an estimator, because we could manually go in and use the transform function on each transformer to push our data frame and our data through that pipeline, and then fit each estimator. But that's a lot of work, in particular where you have hundreds or even thousands of these components. So a pipeline is the abstraction that wraps all of that together and exposes the same estimator interface, where we can just pass in the data to one object, fit it, and we get back a model, which is a pipeline model. So it's the analog to a pipeline, but it's now a fitted model. It has state. Every transformer in that pipeline remains a transformer. Every estimator in that pipeline is a model. So a transformer simply takes a data frame and outputs a new data frame using the transform function. But how do we make transformers? As we've mentioned, when an estimator sees a really great piece of data, they fall in love, and the result is a model, which is a type of transformer. And that happens through fitting. So we'll walk through a simple example. Let's say we want to do some binary classification. We want to see if someone has been admitted or not to college, and we have a few features here. So we first might want to apply a transformer to that to assemble those features, individual columns, into one vector. So that's a vector assembler. We then need to take this string label and convert it into a binary 0-1 label that can be used in our machine learning model. So we'll use a string indexer, which does exactly that. And this is an estimator, so it sees the data, it gets fit, it builds the vocabulary, which is the state, and it returns a string indexer model. And that model can be used on your training data or a new data frame to output the label column. And then finally, we'll train an actual machine learning model, which itself is an estimator. It needs to be fit on training data with labels, and returns a decision tree classification model, which again is a transformer that can output predictions. So putting all of that together manually is not too difficult for 3 stages, but obviously as your pipeline grows in complexity, it becomes very, very difficult to do manually. So we could put it all in a pipeline which looks like this. We instantiate every component, set the stages of our pipeline, and call pipeline fit once on the data frame. And that will take care of all these different components that we saw at once. So now you have an ML pipeline. Your job is done. You can all go home. OK, so Spark ML is great. It comes pre-packaged with a lot of things for doing feature pre-processing, extraction, transformations, dimensionality reduction. And these are normally fairly straightforward. Some of them are more complex, but quite a good place to get started when trying to understand Spark ML and how it works. And of course, traditional ML models, distinct from the Spark kind of model abstraction, which is machine learning algorithms for classification, regression, recommendations. Anything that is not in Spark, and it's quite difficult to kind of get things in there these days because it's a lot of maintenance work and so on. But many things live outside of Spark, in Spark packages, Sparkling ML, which Holden will talk about, but possibly not your amazing custom component that you can't find anywhere and that you really need. And that's what we'll talk about a bit later, how to solve that problem.
Okay. So what is and why Sparkling ML? So not everything can live inside of Spark. This is probably for the best. Spark is already a pretty big package in and of itself. But so Sparkling ML is a place for useful Spark ML pipeline stages to live that are not part of Spark Core. The reason for this is maintaining your own Spark package involves a non-trivial amount of work of keeping it up to date, remembering to do releases and all of these things. And the idea is that if we sort of share this workload together, we can more easily share our cool feature preparation or machine learning stages with the community, and you can all do free work for me. And we can have an awesome machine learning thing, and I don't have to review a whole bunch of code going into Spark, and neither does Nick. Instead, we have to review it going into a different package, but with a little more flexible standards. The other one is I care a lot about the Python community. And it's part of my idea is it would be really useful to expose some of the Python transformers into Scala, which is historically not something that's made a lot of sense. But if you watched the keynote yesterday, you saw about the performance speedups coming to vectorized UDFs in Python. And so this massive speedup means that exposing Python machine learning stages actually becomes a reasonable thing to do because there's a lot of really cool Python libraries, and making them accessible to Scala users is kind of nice. And so now begins our adventure to add stages. Miffy is going to take us on our adventure. She's from Amsterdam, so she's been around a lot. So what does a pipeline stage look like? If you're writing it in Scala, you have to provide this function called transformSchema. We'll talk about what that does in a little bit. But regardless of if you're writing this in Python or Scala, you have to provide either a fit function if you're making an estimator, or a transform function if you're just making a simpler transformer that doesn't have to be trained. Often these things have parameters for configuration. This is very important so that when things go wrong, it is someone else's fault. They did not set the parameters correctly. If you do not provide any parameters on your pipeline stage, it is your fault when it works incorrectly, and that is not a good place to be. More seriously, you want people to be able to control the regularization parameters and have tuning knobs without having to talk to you to push a new version of your package. So transformSchema is used to essentially, if things are going to go wrong, try and catch them. Admittedly, it catches them at runtime. So if you've worked with data frames, you know that data frames are not sort of strongly typed on their contents. And so transformSchema is used to validate the runtime schema that is provided to your pipeline, that it will actually fulfill all of the needs for all of the pipeline stages you've constructed. There are some really wonderful people in San Francisco who are working on making a compile time typed version of the Spark ML APIs, and I am trying to convince them to open source it. However, we are at the stage where they will still not let me say their name, so we've got a bit of a ways to go. But I'm optimistic that we'll get there, and we'll ideally be able to get rid of transformSchema and just use compile time typing. But for now, failing at hour 1 is a lot better than failing at hour 48, unless I'm selling you compute resources by the hour, in which case, go ahead, fail at hour 48. For Python users, transformSchema is not a thing that's implemented. Instead, what you do to get a similar effect is you run a small sample data frame through, and you sort of train on some maybe 10 or 100 rows just to make sure that it's legitimate and things are going to work out for you. So the simplest transformer is going to be word count. And you may have thought that coming to Spark Summit, you would get away from the word count examples, but as a licensed big data instructor, I am always going to show you word count. I enjoy my big data license, and I don't want anyone to take that away from me. So this sort of shows some of the boilerplate, and thankfully it's really not that much boilerplate for making a transformer. We can see we have to have some UID so Spark can track it separately. We have to have some copy functionality. Because we're not doing anything weird, we can just use the default copy, but it has to have an ability to copy itself. And the transform schema, if we were working in Scala, this is what we have to do. We have to validate that our input type is actually present. Actually, strictly speaking, you don't have to validate that your input type is present. If you don't, you're just a bad person, because your pipeline will fail at runtime in hour 48, but it will possibly succeed if the data is present. But the part which is really non-optional is adding it. You have to add your result to the schema. And traditionally, in Spark ML pipelines, we add columns. We don't normally take them away. And the idea is that just because I've made a feature out of something beforehand, I might want to make a second feature off of the same input. So I shouldn't throw it away because it might actually be useful downstream. And we could think about this if we had different ways of like tokenizing or doing some text processing on some input. This is where we do our important business logic. Here we count the number of words. We don't even count the distinct words, but we just count the number of words. You can put really whatever you want inside of here. This is where you put your prediction function or whatever it is you need to do. In Python, it looks pretty similar, except instead of just manually tokenizing it, what we're going to do is we're going to go ahead and add 3 to the number. Realistically, what you would probably do in Python is your function would call numpy or scipy and do something really cool inside of there, and you can use whatever Python libraries it is you need to use in your UDF. Your stages, you want them to be configurable in the standard way. And the reason for this is instead of just using regular class parameters, when you make them configurable with this parameter interface in Spark, Spark's meta algorithms like cross-validation and the parameter grid search can be used in combination to try different parameter inputs. Admittedly, parameter searches on your output column, probably not that likely. But if you had something like a regularization parameter, you might actually want to try and see if it actually impacted your results when you tried the different numbers. And just in case you really miss the 90s, we provide these wonderful setter functions just so that you can feel like you're writing Java beans, which I know occasionally I miss Java 2 Enterprise Edition. In Python, it's very similar. For parameters which are already provided in Spark, the nice part is because they're in Python, we couldn't make them private, so you can just go ahead and mix them into your class. You can still define your own custom parameters, though, as well, so we show both here. And once again, we have the setters and getters, just like Java Enterprise Beans. And so we configure it this way to allow meta algorithms to work. The copying of the input column parameter, the fact that we all copy pasta this all the time, or like the other previous talk which I saw, put their class inside of package org Apache Spark, which just made me a little sad on the inside. But if I admit it, I do it too in my own code. So we're actually going to change this for Spark 2.3. The shared parameters are going to be a public developer API, so you can just mix them in Scala as well, but that's not going to happen for at least a few months. But you're good with that change, right, Nick? We can merge that.
Yeah.
Okay, cool. Yeah, so we'll get that merged after this talk is finished. So cross-validation, yay! This is the TLDR of I did not do very well in statistics class, and most of my machine learning is not very mathematically principled. So I just use it to automatically fit my model parameters, pretend I didn't do that, and tell my boss we've got this wonderful model. Really, the TLDR is thinking is a lot of work. Even if you do have a strong sort of principle basis on which you've selected your parameters, it's probably worth exploring how other parameters perform on your model, or you can also just use the cross-validation thing to compare different model types as well. Here's an example of parameter grid search. This is what you get to be able to do when you conform to the standard. The nice thing here is if we've got a bunch of different parameters on different estimators in the same pipeline, we can actually search over that cross product of parameters. By nice, I mean excellent way to burn a lot of CPU time. If someone's wondering why they're paying for this giant cluster, I can go ahead and do a parameter grid search across 10 parameters, or it'll take a very long time. Yeah, and now over to Nick for the exciting stuff.
We've seen how to create a transformer, which effectively doesn't have any state in it. But how do we make an estimator? So it's very similar, a little bit more complex. So we need to create both an estimator and a model, so a pair of them. The estimator implements fit, which returns the model once it's seen all the data. And model is a transformer, so we need to implement transform. SparkML does give us a couple of tools and basically a predictor hierarchy for various types of machine learning models, regressors, classifiers, and so on. And that takes care of a little bit more of the boilerplate involved in fitting. And we just implement a train method, which is just, the pure training logic, and it takes care of prediction. So it's also a good idea to look into the Spark internals. The code is open, obviously. And you can check out all the develop API traits that are available there for making new predictors. Okay, so how do you make this train function for your new machine learning model? The short answer is avoid it if you can, unless you are a machine learning researcher. You don't want to spend months and months and months implementing some new model from a paper. Of course, if your boss pays you for that few months and you can do that, that's great. But hopefully you can go and find your solution elsewhere out there. But if you do need to do it, and sometimes you do for various reasons, or maybe we want to implement some sort of meta algorithm, then we're going to walk through how to implement that now. Okay, so one example of something you might want to do, which is not too complex and is not really a new machine learning model, is an ensemble of some form. So sklearn has this great thing called the voting classifier, where you can combine a bunch of disparate classifiers and get them to vote on a result. So it's a simple ensemble, and we're going to implement something equivalent in SparkML. So we have a voting classifier, which obviously extends the classifier. We need to provide a few types there. So vector is the type of feature it takes, which is commonly some sort of vector. Voting classifier is the estimator. You need to specify that. And voting classifier model is the model. You need to specify that to ensure that you can't return any strange model that is not a voting classifier. So what's important here is we've got the classifiers parameter, which is just an array of the different types of classifiers. So that could be a decision tree, logistic regression, support vector machine, naive Bayes, whatever you want. And here's the train, so really simple. We just want to take each one of those classifiers, fit it on the data set, and we get back an array of models. And we pass that, which is effectively now our state, our trained models, we pass that to the voting classifier model. I'm not saying that this is the most efficient way of doing it, but it is the simplest. And our friend the transformer is now back. We have a voting classifier model, which extends classification model. Again, it's just a transformer with some additional methods. We have to specify a few things. If we're doing binary classification, the number of classes will be 2. And here is really the meat of the whole thing. So we only need to override one function here, and that's predict raw. So that'll take the feature vector and predict the raw kind of class probability, or depending on the classifier type, it'll predict some raw estimate of what the class will be. So we just create a little array, and we go through each of our models, and if it predicts 1 or true, we add that up, and if it predicts 0, we add that into a different part of that array. So as you'll see, we've got this magic method, bending Spark ML to your will. As it happens, the way that the sort of Spark private stuff works here, we had to kind of hack around that a little bit, and that may involve a little bit of reflection in there, and multi-class classification and soft voting is sold separately for extra support contracts. Mm-hmm. And then we just return a vector with those summed up probabilities. And the rest of Spark's tooling just does all the work for us for prediction. So at prediction time, it'll just do an argmax. So it'll find effectively which one of the zeros and ones has the most votes. And we've implemented a majority vote classification ensemble. Okay, so once you've built something new and fancy, what can you do with it? Well, because it's just a pipeline stage, you can throw it into a pipeline. It'll interoperate with everything else in the ecosystem. You can do hyperparameter tuning. And if you have some energy left over, you can write the persistence framework to save and load that thing. And you can even try to serve it in production, though we don't recommend that unless you've had a lot of coffee.
Right. And so getting back to the Python and Scala being friends part, and I really hope this timer is wrong, but we've made it so that to copy the parameters over, it's a little ugly because it's general case, and I didn't want to specify it specifically. So you define your function, and it takes in a var arg of args, and then you have your inner function, which is the one actually responsible for the transformation. And so here you can see we're using spacey, and then the spacey tokenized to dictionary logic doesn't fit on the slide, but essentially you can put your inner transformation inside of here, and now you can share your wonderful Python code with your Scala colleagues, and they don't have to like try and manually rewrite your really cool NLP stuff using kind of not so great Java libraries. No offense to the Java NLP libraries that are out there, but spacey's pretty rockin'. Going in the other way, maybe you might have something that's more efficient implemented in Scala. This can certainly be the case quite frequently. Or alternatively, you have something that was implemented in Scala that they didn't bother to expose in Python. And so here you can see what's happened. Oh, actually, it works better if I point up here. The package name, this is just the name of the package that I'm working in. My class name is the class name of my Java transformer. And it's really easy. The sparkling Java transformer just wraps all of this for me, and it hides all of the terribleness that is Py4j. Or delightfulness, depending on your views on inter-process communication. And it just makes this available, and now you can set and configure this ML pipeline stage just as if it had been written in Python, except it's going to run in the JVM. And this only really becomes problematic when it breaks, and at that point, as Nick was pointing out, you buy a support contract. Or more realistically, you open a GitHub issue, and we take a look at it. And so this isn't just like, as you've probably figured out since there's 3 talks on the same topic, implementing these things has become sort of a cottage industry is the wrong word since it's all free, but a cottage hobby that somehow we convinced our employers to pay us for. So XJBoost is exposed. The feature transformers, I work on the Lucene transformers and spacey being available as custom libraries. If you're trying to raise money in San Francisco, there are deep learning libraries available. MXNet and DL4J both implement this interface. The Intel one only implements part of this interface, so I'm upset with them, but at least they implemented part of the interface, so they're not bad people. If you're actually interested in doing this, of course, the best thing to do is go out and buy several copies of my book, because we do cover it in one of the chapters. Alternatively, you can look at the models in Sparkling ML, the models inside of Spark itself. I have an O'Reilly radar blog post that goes into this in more detail with code examples as well. There are a large number of Spark books. There was a time when this slide was all of the Spark books, but I can no longer fit all of the Spark books on a single slide. And I think this is a very good sign for us. So naturally, I've kept the ones where I either owe the person a favor or I make money. And so if you're completely new to Spark or you've got a friend who's just getting started in Spark, I think learning Spark is pretty good. If they're a Python user, learning PySpark is a really good one there. But really the most important one is this book. And this one buys me about 1/4 of a cup of coffee. So if you're gonna buy it with your corporate expense account, I recommend buying at least 4. You know, it's good. One for home, one for the train, and one for work. And then an extra one just in case any of those go missing. It's big data. We need to be able to have hot swap. If you want an excuse to come visit any of these places, I will be going to most of them. Actually, all of them. Possibly Spark Summit. The CFP isn't open yet, but I'm hoping that they continue to have me back, and you can see me at future ones. And Nick is going to be hopefully at some of these as well. I think
Strata and Spark Summits.
Hopefully Strata and Spark Summit, yeah. And I'm trying to convince him to come to Singapore, but it's not working out. I think we're running out of time based on TD standing up. So if you have questions, you can come find us outside. I'm wearing a gold sparkly dress. If you don't come find us outside, I will be downstairs drinking coffee. and you can ask me questions there. So thank you all for coming.
Thank you.
I have nothing more to say. We actually have run out of time to ask questions. So
Oh, we do? Oh, okay. Oh, there's some microphones
there
here.
are some, so maybe one question now and the rest outside the door.
Hi.
Oh, hey.
Hello. I had a brief exposure to the estimator and transformer model. And transformers seem to be like very easy to create and extend. You have the unary transformer that really gets you up and running very fast. When you go to estimators, then you are on your own most of the time. That you have to rebuild. There is a lot of things that are given to you, and when you want to create a model, they are not available anymore. They are all private. Is that changing? Is that evolving and making some of these like all the parameter handling is private and should be kind of accessible?
So we're working on making more of those things public. Nick and I are going to make some of them public this afternoon. And for the other ones, if there's things which are private which you want to be public, like email me. And if no one's looking, I'll do what I can.
Okay. And what about the hierarchical construction of transformers and estimators? They seem to be like a kind of line of abstract classes that extend each other, and then they really tie your hands in the kind of things that you can mix in at any point in time. That like seems to me, I said it's brief, that the contact I had with that code base, but that it should be broken down into kind of traits that can be mixed and be a more extendable.
That is probably not going to happen. Okay. Just from a point of view of API compatibility, for the Spark 2 line, we're probably not going to be able to change those. But if you've got ideas about what you want to see refactored there, I mean, Spark 3 will happen eventually. And I have a bunch of things I want to refactor for Spark 3, but if we want to talk, we can make a wish list for Spark 3 ML refactoring. Right. I know Nick probably has some things he already wants to get in there.
We're very keen to make it easier for people to extend Spark ML. And I think all three of the talks have highlighted in some way that there are definitely gaps, there are things that need to be opened up, made developer API, simplified. So any suggestions for that, particularly for the 3.0 kind of time frame, would be welcome. Yeah.
All right. Thank you very much.
Thank you all for coming. We'll do more questions outside.
Yep.
Yeah, we'll do more questions outside. Thank you.
Follow the golden Sparky dress.